Okay, good morning, everyone. Hi. Okay, so we are considering the differentiation rules, and we just completed first the six sections. So before we go to the next one, let me brush up. Okay, let me review the formula. Okay, so let me review some materials. Okay, so here is okay. So okay. So, okay, we first consider the following formula. So when we differentiate, so the differentiation, okay, when I say the differentiation, it has three meanings, right? So mathematically, the f prime of x is defined by the limit of f x plus h minus f of x over h, and then you let h go to 0. So if that limit exists, then we call that limit by f prime of x. And secondly, it measures how fast the function changes at the point x. In other words, that is the instantaneous rate of change of this function at point x. Or when you draw the graph, this f prime of x represents the slope of the tangent line at point x. Oops. So sometimes it is convenient to use the mathematical definition to talk about the derivative, but in applications, right, in engineering or in economics, the instantaneous rate of change of the function at a given point might be more useful in some situations. And sometimes you need to combine everything with the graph. And at that point, the f prime of x represents the slope of the tangent line at a given point. Anyway, you need to remember these three meanings. And then when I consider the constant, its derivative will be always 0. And when I consider any power function, x to the n, then at this point, this n can be any real number. Please remember that this n can be any real number. That it doesn't have to be an integer. Okay. So given any real value n, x, when x to the n is differentiated, the derivative will be n times x to the n minus 1. And e to the x, e is very special, as we will see in a moment. E to the x is very special, so that the derivative will be the function value itself. And when some constant is multiplied to a function, its derivative is c times f prime. And this sum or subtraction can be performed before the differentiation or after the differentiation. And then we have the product rule. Please be careful, okay? So let me highlight the one you need to be careful. So when you consider the differentiation of a product of two functions, you need to differentiate one function at a time. Okay, so that is important. And then when you consider the derivative of the quotient, you first differentiate the numerator, okay, times the denominator minus the numerator times the derivative of the denominator. So at this point, you need to subtract the second term from the first one. And then the denominator is the original denominator squared. So this is the basic rules of the differentiation. And then we extend it a little bit. We consider the rate of change of the trigonometric functions. So when sine is differentiated, you get cosine. And when you differentiate cosine, you get negative sine. And then when you differentiate tangent, you get secant squared. So you need to be familiar with these derivatives. Of course, you need to know how to differentiate cosecant, secant, or cotangent function like this. So because after the middle term, yeah, we will consider a little bit of integration before the midterm, and at that point, this differentiation formula will be used again. So you need to, if possible, you need to memorize them. Otherwise, you should be familiar with all the rules so that when you write down on the paper, on the cheat sheet, you should be able to find them easily. And right, so please be familiar with these rules. So this is the basic derivative of the original trigonometric functions. And then when I derive those differentiation formula for the sine or cosine, I need to consider the limit of sine theta over theta as theta goes to 0. And the limit was not 0, not infinity, but 1. So please remember this. And when you consider the limit of cosine theta minus 1 over theta, it is 0. Okay, and anyway, I will prove this formula, okay, soon, okay, soon. But, and previously, as I said, I derived this, we could derive this formula using the geometry, but let us prove with some more simpler formula. But anyway, you need to remember the results of this. And then we have the one of the most important formula in differentiation, which is the chain rule. So when you have a product, I'm sorry, when you have the composite of two functions, f of g of x, its derivative will be the derivative of the outer function evaluated at g of x, the inner function, multiplied by the derivative of the inner function. So this is one of the most important formula in the differentiations. And I will show some examples after I talk about these rules. So one of the usage of the chain rule was the derivation of the derivative of the exponential function, right? So I could do some manipulation of the exponential function and could derive the following formula. So when you differentiate b to the x, you get b to the x multiplied by log of the base. So ln(b) is multiplied. Okay, please remember this. And at this point, when I derive this formula, I use the property that any number can be written in this exponential form with base e. So using this, I could prove the derivative. So I could derive the formula 5. So at least you need to remember the formula 5. So whenever you differentiate b to the x, 1 ln(b) appears. And then we considered implicit differentiation. So when I say an explicit function, that means this variable y is given in terms of x. So some explicit representation, say y is, say, the arcsine of, say, x squared plus 1, something like this. So on the right hand side, we have pure expression in x variable. So when y is given in that way, then we say y is an explicit function of x. And then we could apply the formula I just introduced when y is differentiated. But sometimes we are given some relation between x and y. For example, for example, say sine x plus cosine y equals to, say, 1, something like this. So some equation is given in both x and y, and if you want to find the instantaneous rate of change of y variable in terms of x, then you need to apply the implicit differentiation. So implicit differentiation can be performed by just differentiating this equation directly. In other words, you just apply this differentiation operation on the left hand side and the right hand side, and then you equate them. So you need to differentiate both sides of the equation with respect to x. And then what did I tell you? You need to move all the terms having dy dx to the left hand side and all the others to the right hand side, so that the terms on the left have dy dx in common. Then we can solve the equation for dy dx, because every term on the left will have dy dx. So I can combine them using dy dx as a common factor, and then the resulting coefficient. Using that resulting coefficient, you divide the equation. Okay. So I will introduce some more. So for example, if I consider this equation above here, so the first step is you need to differentiate the left hand side and right hand side, and then you equate them. So you given sine x and cosine y, you differentiate this with respect to x. Okay, you always differentiate with respect to x, not y. Okay, and then you also differentiate the right hand side. In this case, 1. So when I differentiate the first function on the left, when sine is differentiated, you get cosine x. When you differentiate cosine y, you need to remember that this y is some function, even though we do not have an explicit representation of this sum. Okay, So when cosine y is differentiated with respect to x, you need to apply the chain rule. Okay. So at this point, remember that y is a function of x. So you need to apply the chain rule. So the next term, when cosine y is differentiated, you first differentiate the outer function, which is negative sine. You evaluate this at the inner function, which is y. But that's not the end of the chain rule. You need to multiply the derivative of the inner function. That is dy dx or y prime. And that must be the same as the derivative of the right hand side, which is 0. Now, cosine x doesn't have dy dx, so you move that cosine x to the right hand side while you keep negative sine y dy dx on the left because it has a dy dx. So in other words, you get negative sine y times dy dx equals negative cosine x. So by dividing this equation with the coefficient of dy dx, which is negative sine y, so dy dx just will be negative cosine x over negative sine y, so that you get cosine x over sine y. So that is the instantaneous rate of change of this function y with respect to x. So that's an example of an implicit differentiation. And then we consider the derivative of the logarithmic function using the implicit differentiation. So the derivative of log of x with base b, we get 1 over x times ln b. And when b is e, you get the natural logarithmic function, and its derivative is simply 1 over x. So please remember that when b to the x is differentiated, you get b to the x times ln b. So ln b is multiplied, and when b is e, you get the derivative of e to the x is e to the x. Now, when you differentiate log of x with base b, you get 1 over x divided by ln b, and when b is e, you have just 1 over x. So this is very important formula. You need to remember this. Of course, you need to remember the derivatives of the exponential functions as well. And then we have one expression for e. So as n goes to infinity, okay, 1 plus 1 over n to the nth power will go to e. So here N doesn't have to be an integer. N can be any number which increases to infinity. Okay. Then 1 plus 1 over n to the n will have the limit e. So how did I introduce e in the beginning? We considered the tangent lines of the exponential functions at 0. And then we observed the slope of the tangent line at 0, right? So the slope changes as the base b of the exponential function changes. And at some point, the slope of the tangent line will be 1, and we selected the corresponding b as e value. That's how we differentiate e. In other words, e is chosen so that the exponential function with base e has the tangent line, okay, at with slope 1 at 0. That's how we define e. Now in this slide we have some mathematical way to derive the value e. Actually, the Euler calculated this value by hand, and he confirmed that the limit exists. Anyway, e can be defined, e can be obtained by this limit. And then we considered the inverse of the trigonometric functions. So we considered the differentiation of the arcsine, arccosine, arctangent, and so on, right? And also we could consider these. And for your information, how did we differentiate this, derive this? For example, how did I differentiate the differentiation of the arcsine? Well, I defined E to represent this arcsine of x, and then instead of differentiating this function directly, so that implies that sine y is x, and then this left hand side is the composite of two functions in x, and then I considered implicit differentiation. And for the left hand side, I apply the chain rule. So by applying the chain rule with implicit differentiation, the differentiation of the left hand side with respect to x, you get cosine y multiplied by y prime equals to 1, right? Do you remember this? And then y prime was 1 over cosine y, but that result still has some minor problem because this y is the variable I just introduced myself. So y is my own variable you didn't give me. The textbook didn't define y variable. So this 1 over cosine y, then nobody knows, okay, the meaning of y. So I want to replace this y in terms of some expression in x variable. So I remember the fact that the cosine y and sine y make some simple identity. And cosine y squared is 1 minus sine y squared. Then cosine y has two possibilities, right? So at that point, cosine y has two possibilities, plus or minus 1 minus sine y squared. Now, now at that point, we need to remember one fact, that originally the sine function is periodic, meaning it is not one-to-one. That means it is not invertible in its original definition. But sometimes I want to define the inverse of a function. So this inverse of a function implies that your sine function is one-to-one. In other words, the domain of the sine function must be restricted so that the sine function becomes one-to-one, and so that we can think of its inverse. So when I think of this arcsine, the inverse of the sine function, the value, the y variable, must be restricted between minus half pi and half pi, so that the function becomes, sine function becomes one-to-one. Please remember on that interval, your sine function will be one-to-one. I mean, so this is the graph of the sine y. And on that interval between minus half pi and half pi, the graph of the cosine is this. This is the graph of the cosine y. In other words, cosine y is always non-negative between negative half pi and half pi. So in this plus or minus sign choice, your choice will be plus sign, so that the cosine takes the positive non-negative function. So you get 1 over square root of 1 minus sine y squared. But sine y is just x. So we get 1 minus x squared in the denominator. Right? That's how we can define, how can, that's the derivative of the arcsine function. You can apply the similar trick to derive with the other six, the other five, and you need to remember this formula, especially the inverse of the derivative of the inverse. You need to memorize all six. Actually, if you take the calculus class, I mean regular, the not reg, this is also regular class, but the class for all the freshmen in Korea University, there is no cheat sheet, meaning you need to memorize all these formula for that course. But in our class, okay, I'm just giving you some, you know, hint, so you can use the cheat sheet. Anyway, you need to practice this formula. Okay, just a second. Let me check the. Oh. Okay, I got a question asking when will be the first assignment posted, but there won't be any assignment in this class. Okay, anyway, so those are what we considered so far. And okay, let me open the textbook and consider some examples. So far we considered many formula. So as an example, if I have, say, the f of x defined by sine ln x. So I have the composite of two functions. Then f prime will be the derivative of the outer function. When sine function is differentiated, you get cosine. And you evaluate that cosine at this inner function. So cosine ln x multiplied by the derivative of the inner function. So if I differentiate ln x, you get 1 over x. So cosine ln x over x will be the derivative of this function f. And what is a little bit challenging? Okay, so okay, then how about this? The gx is e to the x squared times ln x. So the exponential function and the exponent is some function, a product of two functions, x squared times ln x. So if I differentiate this exponential function, the derivative of so this is another composite function. The outer function is the exponential function. Its derivative will be the exponential function itself. And you evaluate that exponential function at the inner function. So e to the x squared ln x. And then you multiply the derivative of the inner function. I mean, right? Which is the exponent. Now, this exponent is the product of two functions. So you need to differentiate the function one by one. So when I first differentiate the x squared, then you do not change the ln x function. Plus, the next time, so it's time to differentiate the ln x. But in that case, you do not touch x squared. So x squared times the derivative of ln x. So we get e to the x squared ln x times the derivative of x squared will be 2x times ln x plus x squared times derivative of ln x is 1 over x. So we get 2x times ln x plus x. Now x is a common, so you can rewrite this as x times 2 ln x plus 1. So that will be the derivative of the gx function. Okay. So at this point, x squared and ln x are multiplied, right? But what if I slightly change the function? For example, so if I define h of x by e to the x squared plus ln x, then h prime of x will be e to the x squared plus ln x is the same, but when you differentiate the inner function x squared plus ln x, you first differentiate the first term plus, and then you differentiate the second term. So you get 2x plus 1 over x. right? And then if you want, okay, so this is one answer, okay? This is one perfect answer. But if you do some manipulation of this result, I can do the following. For example, e to the x squared times e to the ln x and e to the ln x is the same as, please remember that moments ago I just mentioned that any number b can be written as e to the ln b, right? So x can be written as e to the ln x. So if I use that formula, then e to the ln x is just x. And then if I multiply x to these two terms inside the bracket, you get 2x squared plus 1. So this is another form of the solution. Okay? This one or this either is fine. When I give such a problem, okay, you can use any of these two results. So these are some examples. And what else? Okay, we have, okay. Uh, okay. Okay. How about, mm, I like, mm, mm, yeah, how about this? So suppose that y is given at an absolute value of secant x. So we have the composite of two functions. So when I consider y prime, ln function, when ln function is differentiated, you get 1 over x, right? But now I have the composite. So, but this is a change, the composite of two functions. So when I differentiate the outer function, I get the reciprocal function. And that reciprocal function must be evaluated at the inner function. So you get 1 over the absolute value of secant x. So, so I don't need this sec. So I have secant x. And then you need to multiply the derivative of the secant function. So when I differentiate secant function, you get secant and tangent. So one secant is cancelled and you get tangent function, right? So that's the derivative of that function. If you want, you may differentiate one more time. Say y double prime will be definitely secant x squared, right? So in this way, you can differentiate the, the function. What is the third derivative? Well, if the second derivative of is this secant x squared, then this is another composite, right? The power function with power 2 is the outer function, and the inner function is the secant function. So when this secant x squared is differentiated, the derivative of the outer function will be 2 times x. So 2 times of the inner function. So this corresponds to the derivative of the outer function evaluated at the inner function. And then you shouldn't forget the derivative of the inner function, which is secant x tangent x. So 2 times of secant x squared times tangent x will be the third derivative. So in this way, you can compute even the higher order derivatives. And we have some more complicated. Oh, yes. How about uh, this one? Y is given by x to the sine x. So please be careful with this example. Note that this is not a power function. Okay. And this an exponential function. Please remember that in case of a power function, you have a variable in the base, but the exponent is fixed. Exponent is some number, 2, 3, something like this number. In case of the exponential function, the base is constant, like e number 2 or 100, while the exponent is a variable, right? So when you look at x to the sine x, both the base and exponent are variables. So this is not neither a power function nor an exponential function. Okay? So please be careful. Then how can I differentiate this? We do not have any formula for such a function. Okay? Right? I didn't introduce any formula for the differentiation of such a function. So you need to convert the shape of the function into something which we have certain formula. So for example, if the problem is complicated, you need to think of the log function. In other words, you need to apply the log function. So log the left hand side will be the same as log of x to the sine x. And in case of the log function, if I have any exponent, you can multiply that, whatever it is, to the log function. In other words, you can rewrite this as a sine x times log x. So let me consider the natural logarithmic function that is easier. So to deal with, so let me consider ln y, ln, then we get ln x. Now, when I look at the right-hand side, I have a product of two nice functions, sine function and logarithmic function, and those two are multiplied. So I know how to differentiate the right-hand side because I can apply the product rule. So this is a product of two simple functions, which means I can just apply the product rule. Okay, then what is the the left hand side? Y is a function of x, that is what is given, and then I have just a log of y. So that means I have a composite of two functions. So what is the next step? I can differentiate both sides with respect to x. And then for the left hand side, I need to use the chain rule. Okay, so in other words, okay, so I just took the log function to convert the function into a simpler shape. So let us differentiate the left hand side. So in other words, if I differentiate the left hand side, you get the derivative of the outer function, which is the reciprocal function evaluated at the inner function, multiplied by the derivative of the inner function, which is y prime. And what is the derivative of the left hand side? Sine x times ln x. So I need to differentiate each term one by one. So I first differentiate sine multiplied by the next term plus sine function without differentiation multiplied by the derivative of the logarithmic function. So you get cosine x times ln x plus sine x times 1 over x. So that must be the same as this 1 over y times y prime. So 1 over y times y prime will be cosine x ln x plus sine x times 1 over x. Now, our goal is to find y prime. So y prime will be y times the cosine x ln x plus sine x times 1 over x. And what is y? Y was this very complicated function, x times sine x. So if you plug in that expression, we get the derivative of y with respect to x. So that is the derivative of x to the sine x. So what was the procedure? Given this function, okay, so y is x to the sine x. You need to apply this log function. So if your function is very complicated, one hint is apply the ln function to both sides of the equation. So that's how we consider how we compute the derivative of such a function. So one more example, and then let's go to the next section. So if I have, say, y is square root of x to the x, please do not apply the formula for the power function. Please do not apply the formula for the exponential function. As I said, both the exponent and base are changing. If you have such expression, if you have such a function, you need to apply the ln function. So if you need to take ln y equals to ln the right hand side. And then you move the exponent to the front of the function to get x times log square root of x. And actually, the square root of x is x to the 1/2. So 1/2 can be multiplied to the ln function to get x half times ln x. That is ln y. Now you differentiate. So that is the first step. You need to apply the ln function. Second, now is the time to differentiate each side of the equation with respect to x. So if you differentiate ln y, you get 1 over y times y prime. So you always have 1 over y times y prime for such a problem. What is the derivative of the right hand side? X half times ln x. So this is the product of two functions. You need to differentiate each function at a time. So if I differentiate the first function, you get 1/2 multiplied by the second function, log. And then x half times the derivative of the second function, which is 1 over x. So 1/2 of log x plus 1/2. In other words, 1/2 of log x plus 1. So that must be the same as the derivative of the right hand side. So 1 over y prime equals 1/2 of ln x plus 1. In other words, y prime is y times 1/2 of ln x plus 1, and y was the square root of x to the x multiplied by 1/2 times ln x plus 1. So that is the y prime. So this is how you differentiate such a function. Please be careful. So if I give such a problem, really many students make a mistake every year. So please be careful for such a problem. Okay. So anyway, that's probably I considered. Okay, let me just consider just one more function for the inverse of the trigonometric functions. So uh, for example, okay, I have, yeah, um, okay, yeah, so something like this. Say g of x is the inverse of the secant function of e to the x. So if I differentiate this composite of two functions, I first apply the formula for the derivative of the inverse of the secant function. So, and then you evaluate that function at the inner function. So you get 1 over e to the x times square root of e to the x squared minus 1. That was the evaluation of the derivative of this inverse of the secant function and an inverse the inner function multiplied by the derivative of the inner function, which is e to the x. Right? So derivative is just e to the x. then e to the x can be cancelled. So you get 1 over square root of e to the 2x minus 1. So that is the derivative of such a function. How about the next one? Y equals the inverse of the tangent function evaluated at square root of x minus 1. So this is another composite function. So to get the derivative of y, you first consider the differentiation of the outer function evaluated at the inner function, square root of x minus 1. So you get 1 over 1 plus the inner function x minus 1 squared multiplied by the derivative of square root of x minus 1. In other words, you need to multiply the derivative of the inner function. So you get 1 plus, if I square root of x minus 1, you get x minus 1. And then x minus square root of x minus 1. Well, you may think that that is another composite function, or you need to think that square root of x minus 1 is half power of x minus 1. So the derivative of this square root of x minus 1 is 1 half of x minus 1 to the negative 1 half multiplied by the derivative of x minus 1. So you get 1 over x multiplied by 1 over 2 times square root of x minus 1 multiplied by 1. So that is so eventually you have 2x square root of x minus 1 in the denominator, and the numerator is just 1. So that is the derivative of that function. So we considered many examples in the sections, okay? And as I said, please be careful with such function. This is really important, okay? So, and or this. So this is not a power function, so you cannot apply the formula for the power function. This is not an exponential function, so you cannot consider the derivative of the exponential function. Okay, so we considered many examples now. So, but actually, I'm going to introduce another more complicated formula in a moment. But before I expose some advanced formula, more advanced, I want to review. I wanted to review what we studied. Okay, so please practice this formula. And if you have any questions regarding any of these, please let me know. So I will post these examples, or I mean this video recording on the YouTube. So you can just, if you want, you can just double check the video recording. And if you have any questions, please let me know. Please email me. Okay. Anyway, so those were the reviews of first 6 sections in chapter 3. Now, let's go to section 10. Okay. Section 10 is a little bit on application, I mean, which is called linear approximation, meaning when you have a function usually a nonlinear function or a function which is very complicated, you want to introduce somewhat simpler one, usually a linear function, meaning the first order polynomial, to approximate the given function. Okay? So the idea is very simple. So suppose that I have the function f. So I have the function f whose graph is the blue one. Okay, and suppose that I know the function value at a. So suppose that, in other words, a and f of a are known, or at least that f of a can be easily calculated or estimated. In that case, I can find the tangent line at a given point, right? So the tangent line, the red one, can be derived. And as you know, the tangent line is given in the form of mx plus b type equation. In other words, that is the first order polynomial in x. So we call this equation, so using the information at a and f of a, and if if I know that f prime of a can be estimated, then that will be the slope of the tangent line, right? So if I know the value f of a and f prime of a when x is a, then I can find this m and b of Lx function. Now, this Lx function is called a linearization of the given function f at a. So this Lx is called a linearization of f of x at x. Okay. So when x is, so here is the a, and if your x is very close to a, then the value Lx will be a good approximation to f of x, right? Oops. So this point, this red dot on L of x will be a good estimation of the original value on f of x graph, right? If x is near, but if x is far from a, then say if your x is very far, then the value on the linearization and the original value of the function may have large deviation, right? So sometimes for some reason, okay, especially for approximation reason, we want to find the tangent line, and then using the value of the tangent line, we want to estimate, we want to approximate the given function at some point, say x. Okay, so in this situation, the Lx is called the linearization of the given function at point A. And then why do we study this linearization? As I said, I want to approximate the value of f at some nearby point x. That is the purpose. Then is it always good? If x is close enough to a, then this approximation is very reasonable. because the error will be quite small. But if your x is far from a, then there may be a large error between the value of the linearization and the original function value. Okay? So that's all for this section. So as I said, the expression of the tangent line mx plus b is called the linearization of this function at the given point. So your function value at x will be very close to the value of this linearization, and this is an approximation, and this approximation will be quite good enough if your x is close enough, right? But otherwise, if your x is far from a, then closeness may not be guaranteed. But in engineering or in economics, they want to find a certain approximation. Okay, so many people, or even in physics, they consider this a linear approximation, and many physical equations were derived based on linear approximation. So here is an example. Suppose that I have the square root of x plus 3 function, and suppose that I want to estimate these two values. Now, these days, everyone has the calculator, so we can easily estimate these two values. But this is just a toy problem, and we have similar situation in real world. If you consider, say, fluid mechanics, we have similar problem in physics. And in that case, you need to apply the approximation like this one. So let us consider this problem. So suppose that f of x is given. Okay. Now for that problem, I want to use the linearization. But for the linearization, I want to consider the formula with with 1 as the value of a. Because when a is 1, f of a is square root of 1 plus 3, which is square root of 4, which is 2. I can easily estimate the function value. And also, f prime of x is this one. So when x is 1, f prime of a will be 1 over 2 times of 1 square root of 1 plus 3, and that is 2 times 2, which is a quarter. So I can easily estimate f of a and f prime of a. That means I can easily estimate, I can derive the equation for the tangent line. So if I consider the equation for the tangent line, so if you consider this formula, you can easily identify the expression for Lx. So the linearization means when x is near our a value, which is 1, our f of x will be very close to the value of Lx. So what was the problem? We want to estimate 3.98 and 4.03. Okay, so 3 point, so this is, okay, so 3.98 is square root of 0.98 plus 3. So that is approximate to 7. And this 0.98 is quite close to 1. So that will be approximated by 7/4 plus 0.98 over 4. Square root of 4.05 is 1.05 plus 3. So this is also close to 1. So that can be approximated by 7/4 plus 1.05 over 4. So that's the application of the linearization. Okay. And then what else do we have? Then how about f of x defined by ln 1 plus x? And let us consider the case when the x is a 0. I mean, a is a 0. Then what is f of a? That is ln 1 plus 0, which is ln 1, which is a 0. And f prime of x is 1 over 1 plus x times the derivative of 1 plus x. But when 1 plus x is differentiated, you get just 1. So you get 1 over 1 plus x. When a is 0, so f prime at 0 will be 1. So what is the equation of the tangent line? So Lx will be f prime at 0 times x minus a plus f of a. So f prime 0 at 0 is 1 times x minus a. So this is 1 and a is 0 and f of a is 0. So what remains will be just x. So in many applications, for example in economics, this ln m1 plus x may be approximated by x when your x is near a value, when x is near 0. Okay, so this is a very common example of a linearization. Okay? Or in physics or in fluid mechanics, when you consider the Navier-Stokes equation, the original equation is very complicated, but right, because the conservation of mass, momentum, and energy will give you very complicated equations, but you use the linearization to handle this Navier-Stokes equation, right? So those are another examples in engineering or in fluid mechanics or physics, or this ln 1 plus x may be approximated by x. And as I said, this approximation is reasonable when your x is near the original a value 0. But if x is far from 0, that approximation may not be meaningful. Anyway, that is one example of a linearization. Okay, do you have any questions? Okay. Now, I have, okay, so, oh, this was one example of the graph of this previous example. For this function, the linearization at 1 will give you the red tangent. So your x is close to 1, the point on the tangent line will be close to the actual value of the function on the blue curve. Okay, but if your x is far from the a, then there may be some errors. But anyway, okay, so let us take a break for 15 minutes and then let me consider some more new terminology of this section. So see you in 15 minutes.